Hello, welcome back to Math 155. Today we're going to be reviewing graphical analysis of population models in one dimension. And we're going to be focusing on the logistic equation, Allele effects, harvesting models, how we can use these plots to work out equilibria and stability of models as well. Okay, so what we really want to know when we're looking at population models often is what happens to the population over a long period of time. So does the population tend to a fixed point, a steady state or an equilibrium? How can we find these steady states or equilibria? And if the population starts near those steady states, does it tend towards them? In other words, are they stable, or does the population tend away from them, in which case they're unstable? All the models that we look at today are essentially going to be extensions of this exponential growth model, where the rate at which the population grows is proportional to the size of that population at the particular time. So what we're going to do, first of all, is going to look at the logistic equation. And what that does is that says that rather than having a constant growth rate, for example, R0, we have a growth rate that depends on the population size P. We refer to R0 in this case as the growth rate for small populations. So if we imagine that P is very small, this essentially goes towards 0. And so our per capita growth rate of the population is just R0. When the population is larger, this term in the brackets starts to play a larger role and reduces the overall growth rate of the population. And this term K is referred to as the carrying capacity of the population. In other words, the maximum number of individuals that can be sustained. So if we think about a plot of our growth rate RP against population size, well, we know that when P is equal to 0, RP is just equal to R0. We can think of this as our growth rate in the absence of density-dependent competition. And this growth rate RP just looks like this. It's just a straight line. So here in this region, we have R is greater than 0. Above some value, we have R is less than 0. And this value here is when P is equal to K. So when we have a population size of K, our growth rate is going to be equal to 0. When the population size is smaller than K, the growth rate is positive, so the population can grow. When the population has a greater number of individuals than K, then the population size shrinks. And so we can see that the population is probably going to be tending towards this value of K. So if we put in some specific numbers to this, the P's have now been changed to N, but that doesn't matter. Here, our R0 is going to be 1.2. So this value here. Carrying capacity, K, is 4,200, this value here. So although we've changed around, we've got N's now, it doesn't matter. This is still a logistic equation. So when is the population growing? Well, the population is growing whenever we have this term here in brackets is positive. So this means that we need our population size to be less than 4,200. It needs to be greater than 0 because if the population size is equal to 0, then this term is 0, so the population size isn't growing. So the population size is increasing whenever n is between 0 and 4,200. The population is going to be decreasing whenever n is greater than 4,200, because that makes the term in the brackets negative. So what can we tell are the equilibrium solutions? Well, if we start off with no individuals in the population, if n is equal to 0, then dn dt is equal to 0, so there's no change, so that's an equilibrium. We also see that if n is equal to 4,200, if it's equal to the carrying capacity, then the term in the brackets is equal to 0. So again, dn dt is equal to 0. So both of these are equilibria of our system. We can think of this graphically as well by noticing that our dn dt is just some function of n itself. If we go back up here, this right-hand side here, you can think of this as our g of n. It's just some function of n. And so, we can plot that. And so what we're really doing then is we're plotting dn dt versus n. So what does that look like? Well, it's a quadratic with a maximum. It looks something like this. So we can see that we have some interesting points here whenever dn dt crosses the axes. So we see here that this is an interesting point here at 0, this point here when n is equal to 4200. So n is equal to k there, 4200. Now in this region over here, we have dn dt is greater than 0, it's above the axis, and therefore our population size is going to increase. I can indicate that by an arrow on this axis. And over in this region here, dn dt is negative. So that means that our population size is going to be decreasing. We see also that dn dt is going to be equal to 0 at this point here when n is equal to 0, and dn dt is going to equal 0 at this point here when n is equal to k. So what this tells us is that if we start off in some value along this line here, when n is between 0 and k, suppose we're at this value here, that's our n0, we're going to see that our population size increases, eventually tends towards k. Likewise, if we started with some value over here, this was our n0, you eventually see that our population size will tend towards k. If we started off with no individuals in the population, we'll just stay there. So what we can say then is if our n0 is greater than 0, then n of t will tend towards k as t tends towards infinity. Another type of population model incorporates something known as the Allele effect. And in this case, we've modified that logistic equation by this additional term here, p minus a, where a is some constant value between 0 and k. And what this means is that when the population has a sufficiently small value, when p is less than a, this underlying term here is going to be negative, and so our population growth is going to be negative. In other words, the population is going to shrink. So if we set this right-hand side again to be our g of p now, so we're going to plot g of p against p, in other words, our dp dt, we're going to see a graph that looks something like this, where now we've got 3 fixed points, 3 equilibria, where we have this one at 0, we have this one at a, and this one here, and p is equal to k. So it's k, a, and 0. So we see it over in this region, that dp dt is negative. So if our initial population size or population size falls below a, we decrease the population size, so we tend towards 0. If the population size is between a and k, then dp dt is going to be greater than 0, and so population size increases and tends towards k. And in this region over here on the right-hand side, dp dt is negative again. So if we have more individuals than the carrying capacity, then our population size will tend towards k again. So this has all the information essentially that we need to understand what's going on in this model. We can say that if p of 0 is greater than a, then p of t is going to tend towards k as t tends towards infinity. And if p of 0 is less than a, then our population is going to tend towards 0. It's going to go extinct as t tends towards infinity. So drawing these sorts of diagrams is a really powerful way of understanding what's going on in these models without having to do any algebraic analysis. We can generalize this. So this is called a phase plot. And if we have some autonomous differential equation, y prime of t is equal to g of y of t, then the fixed points are all points, call them y hat, where g of y hat is equal to 0. So if we plot g of y, then our equilibria, our fixed points, our steady states, whatever you want to call them, are all the points where g crosses the x-axis, or where y is equal to 0. We can see that the stability of each of these points is going to be given by the direction it crosses the axis. So in this diagram down here, this phase plot, we don't know what the equation is for this blue curve, but we can tell that in this region over on the left-hand side, that our dy dt here is going to be greater than 0, so our population size is going to increase. This region here, we've got dy dt is negative, so the population size is going to decrease. So we can tell that we're always going to tend towards this point here if we are in either of those two regions. This region over here, we've got dy dt is positive. So on the left-hand side, we're moving away from this fixed point, and on the right-hand side, we're moving away from it as well, so it's unstable. And then over here, got a similar picture to we had at the left-hand side of the phase plot, where dy dt is negative. So we're moving towards this fixed point. So what we can do is we can say that these solid markers here are stable fixed points or equilibria, and the open markers are unstable. So what that means is we can work out the stability of our fixed points just by taking the derivative of our growth function, g, with respect to the population, in this case y, and then evaluating it at the equilibria and looking at the sign. So if g prime at y hat is greater than 0, then this means that our y hat is unstable. The reason being, if we imagine a zoomed in version of our phase plot, if this is our y hat, if our g prime of y hat is positive, then that means that over here in this region on the left-hand side, we're going to be moving away, and the region over here on the right, we're going to be moving away as well. So that means it's unstable. If instead that g prime of y hat is negative, and then we end up with y hat is going to be stable. We've now got the opposite case here, where if we zoom in on our phase plot, we can have a picture that looks something like this. So on the left-hand side, dy dt is positive, and on the right-hand side, it's negative, so we're going to tend towards our y hat. It's also possible that g prime of y hat is equal to 0. In this case, it's undetermined. We have to do additional steps, which we're not going to cover in this course, but in that case, we can't tell what's going on. Essentially, we might have a situation like this, where our g just about touches the axis here. So we might have something like this. We might have something like this. Or we could have, say, something like this. That's supposed to be a cubic. So we can't tell what the stability of our fixed point is if our g prime of y hat is equal to 0. What's really going on here is we're doing something called linear stability analysis. So we're looking at the stability of our fixed points by making a linear approximation close to that fixed point, and then seeing whether small perturbations grow or decay. So what we're doing is we're essentially constructing a Taylor series. So we can say, suppose that our g of y hat is equal to 0, then our dy dt is going to equal g of y, which is approximately equal to g at y hat plus y minus y hat as by g prime at y hat. So this bit here is our linear approximation. Okay, now we can do a substitution. So if we let u of t equal y of t minus y hat, and otherwise we're going to change our variables so that we're now measuring how far we've moved away from y hat. Then our du dt is just going to equal dy dt minus dy hat dt. And since y hat is just a constant, this is just going to be equal to 0. So our du dt is going to equal our dy dt. So this is going to be approximately equal to g of y hat plus u, as y, u is equal to y minus y hat. So we're going to have u times by g prime of y hat. And this g of y hat is equal to 0 by definition up here. So what we now have is that we just have du dt is equal to u times by g prime at y hat. And this here is just some constant value. Okay, we're evaluating g prime at y hat, so this is going to give us a constant. And this here, if we go all the way back to the beginning, this here is essentially this exponential growth model here. It's exactly the same thing, right? So we know what's going to happen to this. So this means that u is going to tend towards 0 if g prime of y hat is negative, and it's going to grow, going to tend towards infinity if g prime of y hat is greater than 0. So what's really going on here is we're looking at our fixed point, our y hat, and we're going to look at a value fairly close to it, and we're going to say, is it going to tend towards that, or is it going to move away? So this is going to be our y value. What we want to know is this distance between y and y hat given by u, is that going to increase or decrease with time? So if it decreases, then our fixed point is stable, and if it increases, then we move away from our fixed point, and so it's unstable. Okay, so that's linear stability analysis. The last one we're going to look at today is a class of models that are referred to as harvesting models. And suppose we have a population of fish, say, which grows logistically in the absence of any harvesting. And then we add this additional term here on at the end, which is our harvesting rate. So we're subtracting part of the population, which we are harvesting at a constant rate. So I'm going to change this number here just to make it a little bit easier to 4,800 instead of 4,200. So we have a logistic growth equation, and then we're going to have this harvesting term at the end. So we want to find the fixed points of this and determine the stability. So if we want to work out our df/dt, we can expand this into 3f minus 3f squared over 4,800 minus 2.5f. So this means essentially that we can combine these two terms here. This gives us half of f minus f squared over 1,600. And so what we're really doing is we're rewriting this as another logistic equation. Our growth rate is now half, and the term in the bracket is 1 minus f over 800. So we've adjusted the carrying capacity of this population. So this is just another logistic equation, essentially. So we know how to analyze the stability of logistic equations. We can draw a graph of our df/dt against our population size of fish, f. We see that in the absence of fishing, we'll have something that maybe looks like this, where our carrying capacity was 4,800. We analyzed a model that looked like this earlier. Now when we have harvesting in place, our revised carrying capacity has gone down to 800. Okay, so what this means is that we now have a new logistic equation, essentially, when we're harvesting. So our new stable fixed point is going to be when f is equal to 800. It's going to be stable. And f is equal to 0 is going to be unstable. So this fixed point here, when f is equal to 800, clearly depends on the rate at which we harvest the population. So when h was 0, we were over here. And this point here moves towards the left as we increase h. So we might want to ask for what values of h is the population sustainable. So what we can do is we can look at df/dt is equal to 0 and work out where our fixed points are. Well, that requires that either f is equal to 0, or for this particular model, 2 times by 1 minus f over 50 minus h is going to equal 0. In other words, if f is non-zero, then we can divide through by f. So this is different from the model that we had above, and here h is variable. Okay, so we can reorganize this equation here, and we end up with 1 minus f, let's call this f hat, over 50 is going to equal h over 2. Or we can write this as f hat is going to equal 50 minus 25h. So we write this as f hat of h. So this is just rewriting this equation in terms of f. and then we can call this a function of h because we have our h here on the right-hand side. So it's saying that our non-trivial fixed point, our non-zero fixed point for the population, is equal to 50 minus 25h. And so this is a function of our harvesting rate. And so our f hat of h is only positive if we have 50 minus 25h being greater than 0. In other words, we can say that h has to be less than 2. So as long as our harvesting rate is less than 2, then the population is going to have a non-zero fixed point. In other words, the population is going to have a sustainable harvesting rate. Okay, that's it for today's class. Please make sure you are familiar with all of the terms that we've covered today, in particular what an equilibrium is, what do we mean by an equilibrium being stable or unstable, and what do we mean by a phase plot. Okay, thanks very much.